Yes. Okay. All right.
I don't have
Let's get started.
password,
So
I have a Wi-Fi analyzer, which will let me hack Wi-Fi.
write an expression. Write an expression for the potential difference across a capacitor as a function of time as it charges. How do I do it?
Q over T divided by C.
Or
Q
basically,
of T.
I know charge as a function of time is going to be Q naught 1 minus e to the t over negative t over RC. Okay? I know that expression. That's how a capacitor charges. I also know that Q equals CV, right? C stays constant. Plug it in, solve for V. So all I have to do, voltage is a function of time. Yeah, divide that by C. So I get Q naught over C. Ooh, what is Q naught over C?
Voltage.
Lambda.
Full voltage, right? The full voltage of the battery. So eventually it will reach the full voltage of the battery, right? Huh? V naught, yeah. Okay, just an interesting side note there. 1 minus e to the, who's that?
Go H Rose.
Why was Shirozen?
I don't know. So there it is, that's all it is. Easy one, right?
See, this is like what we need so we can boost our confidence.
Okay. Well, confidence boosted. Now let's try R.
That's easy.
Is it just 0.2?
Huh? 0.2? No.
What do you do like a, okay, here's my toss.
Your guess?
Well, I think you would add up.
Okay.
You
Said like
find
0.5 equals 1 minus e to the, there's like Q naught, yeah. Because at first you said 0.5 Q naught.
Yeah.
Q naught equals 0.5 equals 1 minus e to the negative t. Because it's some t, it's that.
Right.
And then you do another equation, t plus 2. Yeah, t plus 2.
Yeah, basically. Yeah. Okay. Yeah. Alright, so student connects a battery to an RC circuit but forgets to start the timer. For shame. He starts the timer when the capacitor is 50% charged. At 2 seconds later, the capacitor is 70% charged. What is the time constant of the circuit? So basically what I'm going to do is this. Q is a function of time equals Q naught, just writing the same thing out again, e to the negative t over RC. Okay, if I divide both sides by Q naught, basically what I get is Q is a function of time over Q naught, which ends up being the percentage charge. Okay? I know the percentage charge. It tells me at these two times. So, I get 50% equals 1 minus e to the negative, let's call it T1 over RC. Okay? So that's my first equation. Now it says 2 seconds later the capacitor is 70% charged. So 0.7 equals 1 minus e to the negative, call it T2 over RC. Okay? So, oh, and actually let's go ahead and replace these RCs with tau, because it's asking for the time constant. Tau. Tau. Okay. So, count them up. We got 1, 2, 3 unknowns, 2 equations. Our last equation comes from
T2 minus T1.
T2 minus T1 equals 2 seconds. Okay? You skip that step, but it's fine. It's a good. It's an okay skip. Huh?
He put it inside his draw.
Right. Right. I'm saying you went ahead and did that, which is good.
Do we matrix?
Huh?
Can we matrix this?
I wouldn't.
Okay.
Because you can just solve it.
Yeah, this is one that's algebraically solvable. Okay? So, yeah, go ahead and replace T2 with T1 plus 2. Okay? So, let's see. And let's go ahead and rearrange these equations a little bit. So we have e to the negative T1 over tau equals 1 minus 0.5 is 0.5 again. And then e to the negative T1 minus, or plus 2 over tau equals
0.3.
yeah, 1 minus 0.7 is 0.3. Okay, and here it's all algebra. Let's see. I'm running out of space down here. Huh? What? Huh?
He said it. He knows algebra.
That's good. All right. So natural log both sides.
0.2 to both.
Huh?
Could you add 0.2 to the bottom one and then just set the equal to?
You could, yeah, sure. But
I would ln both sides.
Yeah.
Actually,
Wouldn't it be easier to natural log both sides?
yeah, it would be. So negative t1 over tau is natural log 0.5, and negative t1 minus 2 over tau is natural log 0.3.
And then you solve for t1.
Solve for t1.
Why is it minus? Oh, yeah.
So
The-
t1 equals negative ln 0.5
Yeah.
times tau.
T1 equals negative tau natural log 0.5.
And then you plug that in for the other one.
Mm-hmm. So you
subtract
get
2 to it.
natural log 0.5 minus 2 over.
Tau.
Actually, let's go ahead and move that tau over. Equals tau natural log 0.3. Subtract these. Now natural logs, when you subtract them, they divide. So I get natural log
Of 0.5 over
5 over 0.3 equals q.
So then you just divide by whatever that.
Yep.
value is.
Solve for tau. Anybody got it?
No.
Do it! Do it now!
2 over the natural log of 0.5 over 20.
I'm fine. I'm fine. Thank you.
I wonder how that sounds on the microphone.
If we just wrote down 2 over the natural log of 0.5 over 20,
What's that?
we get
Where's
it.
the Q9?
When you divide q as a function of time by q naught, by q to the percentage.
3.915.
What? What is it?
3.915.
Oh gosh. 3.905.
915.
1.5.
You don't want to lie.
1.5 seconds. Time constant is measured in
I
seconds.
second that.
As weird as that is.
What about
Huh? Somehow, I haven't done the actual thing, but it does work out that time constant is measured in seconds.
Okay.
Wait, what is the resistance? What is an ohm? What about
An ohm,
Yeah.
it's a volt per amp.
And then what's a
Hello,
what's
people
a,
watching this
what's a
video.
farad?
Oh wait, no, it does work out. Here, watch. Let's see. Resistance,
Now you have video proof that it's the warm up.
V equals IR.
Oh.
Resistance is a volt per amp, right?
Is this video
Volt
for
per
Wesley
amp.
and Tim?
Amps are charged per time, right? So this is second volt per charge, or per coulomb.
Oh, and then the other one is C over V.
Yeah. Capacitance, because we got Q equals CV. Capacitance is coulombs per volt. So if you multiply these two together, you're left with seconds. That's really cool.
Is that it?
Yeah. So. Anybody have any questions?
Don't you have a question? Speech!
I feel bad for people listening.
Is this video for Wesley and Tim?
And what's his face? Rohan.
He's gonna be watching it. He's like,
Can I have this video because my teachers won't believe me what happens?
You idiot.
It'll be on the website, the Springs Physics website. Okay, so today, really quick, I want to talk about something called electromotive force, EMF. Electromotive force.
right now it's an 8 meg file.
EMF. You'll pretty much always see it written EMF.
Is this where we break
thought it was
apart the word
electromagnetic
so we
field.
can find out what it is?
Well, kind of. This is where we break apart the word and make fun of it. Because electromotive force is actually a terrible, terrible name for this. Okay? Because electromotive force is not a force. Okay? Electromotive force is not a force. It is a voltage. Okay? Electromotive force is a voltage. What electromotive force is, it's the actual physical underlying cause of moving charge. Okay? Yes?
I thought it was electromagnetic field.
No. There may be two EMFs, but this is the one we're talking about, electromotive force. Okay? Electromotive force is the actual physical underlying cause of moving charge. Now, in a battery, usually the EMF is some sort of chemical reaction. Okay? But there are other sources of EMF. Okay? There's solar cells. Okay? Wind power actually turns a magnet inside a coil. We're going to look at that in a lot more detail when we get to electromagnetism. It's going to be one of our fun units.
Wind turbines?
Huh?
Like wind turbines?
Yes. Wind and in fact, all turbines work exactly the same. Coal, nuclear, wind, anything that spins is going to turn a magnet through a coil of wire. Okay? It's called electromagnetic induction, and we get to it. Yes.
You should be like the Hawaiian guy and like repeat every question.
No.
Yeah, do it.
Nah. Okay,
They
so
can hear our questions.
EMF. EMF is a voltage, all right? It's written with a squiggly E, okay, epsilon, just another way of writing epsilon, squiggly E,
Start with electromotive
Like
and
that.
ends with a horse.
okay? So the question arises, how does EMF differ from voltage?
How does EMF differ from voltage?
Okay,
Good question.
whenever we deal with EMF, usually one of the things that's going to accompany it is internal resistance. Okay, internal resistance, not quite like a wire. Okay, think about that little battery. Okay, that little battery, it can only supply so much current at any given time. Okay, it's got, like, let's say, take a 9 volt. Okay, if I took a 9 volt and I stuck it on a piece of superconducting wire, superconducting wires have no resistance by definition. Would that battery give infinite current? No. Okay, it would give very, very high current, but it wouldn't be infinite. So there must be some sort of resistance. Where does that resistance lie?
From the battery.
Inside the battery itself. Okay? It's called internal resistance. Alright? So what it looks like in a circuit is this. Here's my battery. Okay? Now the battery itself has some internal resistance. I'm going to represent that by a resistor either right before or right after the battery. It doesn't matter which one.
Right after. Right after. Now.
Okay? Alright, so here's my circuit. Okay? This guy right here is the battery with some electromotive force. Let's use a 9 volt battery. Electromotive force equals 9 volts. Okay? Here is the internal resistance. Now, internal resistance is usually very, very low. 1, maybe half an ohm. Okay? R internal 0.5 ohms. Okay? And then this is the actual resistance of the circuit, whatever it is, R equivalent, whatever you want to call it.
Can you equivocate them?
Yes, you can. You can wrap this up into R equivalent. So like if this was 50 ohms,
It'd just be 50.5?
right. Yeah, you have two of them in series. So internal resistance, not that hard, but it is something you need to take into account. Okay? Yes.
So yesterday I didn't realize that 2 amps was ridiculous.
Yes.
And then, okay, so what is a realistic number for ohms?
Ohms is actually kind of weird. The realistic range for ohms is actually quite large. You can have a 1 ohm resistor. You could have a million ohm resistor. Okay? The main thing that determines what it's realistic or not is... was that a sentence?
Yeah.
It is now.
You understood it, so it is. Is their power rating. The actual physical component, its power rating. If I took this, if I took my hair, okay, my hair probably has a resistance of a couple million ohms, okay, but if I try to run any amount of power through it, it's gonna blow up, okay, not very big because it's a piece of hair, but
What happens if you get a burn?
yeah, that's exactly how it works. You just stick a charge on there, it repels, and you're good. But no, so my hair has very high resistance, but it's not rated for very many watts. Okay.
What if you have Asian hair? Like real
Likewise, you can have very, very low resistance, but again, not rated for very many watts.
if you're a woman.
If you go to, there's a
Hey, my apartment's right there. You can
Yeah.
come visit me.
okay. They sell all sorts of electronic components. They have 1 ohm resistors that are rated for like 1 or 2 watts. That's a stupid lot of power.
What?
Okay?
Are you talking off medical center?
Yes.
Yeah, I live right by there.
It's a fun place. Okay? Anybody have any questions?
Oh yeah, I moved. Don't tell me.
Yeah. All right.
Let's go, Mr. Robert.
Now,
I'm supposed to go shoot.
one thing you'll see asked. One thing you'll see asked. One thing you'll see asked very often with batteries is, what is the battery's terminal voltage? Okay? Because this 9 volts is an ideal. Okay? Your battery is not going to give 9 volts. Okay? It's going to give a varying amount of volts depending on the load you put on it. Okay? Yes. Alright? The greater the load, the closer you get to 9 volts. Okay? A very, very small load, and it'll start getting weird because this internal resistance becomes a larger and larger percentage of it. Does that make sense? Okay. So, what we have here, because the internal resistance is part of the battery, I can draw this like imaginary box around this. And that's essentially my
Like
battery.
Gaussian circuit?
Okay? So this would be the positive end of my battery, this would be the negative end of the battery. Okay? If I put a voltmeter across it, that's where I could touch. I can't reach inside the battery and measure the voltage here. Okay?
With like a physical 9-volt battery, so it's not that the whole thing is in the battery. There's
Yes.
a component inside that's the battery.
Mm-hmm.
What's the other step besides phosphorus?
Well, actually, if you open up a 9-volt battery, there are 6 quadruple A cells in there.
Oh, really?
Uh-huh. And they're each 1.5 volts. Yes. Quadruple A size. The naming, the A's and B's, that's all size information. Huh?
What's a watch battery?
A watch battery? Oh gosh.
Isn't it like a studio?
It's got like a big code. Yeah, not all of them have pretty letter
The code
names.
WATCH.
It's a CR
That'd be cool.
2016.
Is that what it is?
That's what mine is, CR2016.
Sounds right. Okay, so they're asking what's the terminal voltage here. Alright? Now obviously this guy's still going to be 0 volts because he's connected to the 0 volt plate with nothing in the way. But this terminal right here is going to be something different. Okay? So let's figure out what that is. First thing I'm going to do, figure out the current running through this guy. So V equals I times R. R is 50 volts. Well, 50.5. 50.5 ohms. Whatever. So what is the current running through this guy? Somebody figured out real quick.
50.5.
Yeah, 9 over 50.5. What is that?
5.61.
5.61. Okay?
No, that's not right.
Not right.
There's no way.
It's like 0.2.
Point one seven eight.
I did it backwards.
Point what?
0.178.
Okay.
0.178.
0.178 amps, okay? Now I'm going to use that current, figure out the potential drop across that resistor. V, the potential drop, equals I 0.178 times 0.5, the resistance. What is the potential drop?
0.9.
0.089.
No.
0.089.
Okay, so the actual voltage that I will measure across this battery will be 9 volts minus this, 0.089. Okay? So 8 point stuff.
911.
8 something.
911.
Yeah, but that was like the time.
They're right. 811.
8.911
There we go. 8.911 volts.
is the
Okay.
what?
That is what if I took a voltmeter and I measured across here, that's what I would measure. Okay?
205.
Okay, so
Oh,
everybody
no,
kind of
no.
got an idea of what internal resistance and terminal voltage is? Okay.
Is it just within that little part of the battery?
What's that?
That's just what's just in the battery.
Mm-hmm. Now, one thing to know about terminal voltage, it is not constant. Terminal voltage is not constant. Terminal voltage depends on this guy right here. Okay? Terminal voltage depends on the equivalent resistance of the circuit. So, don't think once you found terminal voltage, it's that forever. Okay? Yes. Just stretching. All right. I think that's all we got. Now we can curse.